Good morning. I'm here to speak about quantum computing. Now, this is a very different type of computing. If you think of your smartphone, your laptop, maybe the servers that run the cloud, those are what we call classical computers, which makes them sound old. And in fact, that technology goes back to about 70 years ago or so. Quantum computing has been in the news quite a bit recently. People are hoping that it will be able to do wonderful things. And in fact, it has come very far, very quickly in just a few short years. So I'm going to give you an update on quantum computing, tell you a little bit about how it works, talk about some of the use cases, and then tell you about the momentum. Who is really using this and what are they using it for? So I'm going to start with really a very simple problem here. Now, I'm lucky to speak in the morning. This is the caffeine molecule. There's a good chance many of you have had many caffeine molecules this morning in your coffee or in your tea. It's not a very large molecule, as you see. It only has 90 some odd electrons to it. But I'm going to ask a very simple question, which is, if I were to take this molecule and exactly simulate it in a computer, right? Not approximate, exactly simulate this molecule in a computer, how much information is there? Put another way, how large a database would you need to have all the information you needed in a computer to pretend that you had a real molecule and then could make it interoperate with other things, such as what it does to your brain to wake you up every single morning? Well, the information may surprise you. It's not 1 megabyte or 1 gigabyte or even 1 terabyte. The amount of information just to store the information about the energy configuration is 10 to the 48th bits. So a bit is 0 or 1, 10 to the 48 is 1 with 48 zeros after it. Okay, how big a number is that? Well, scientists have estimated that the number of atoms in the Earth are between 10 to the 49th and 10 to the 50th. So the number of zeros and ones needed to represent just one caffeine molecule, and remember, you have thousands in you right now, probably, right? But just one molecule at one instant could be as much as 10% of the number of atoms in our whole planet. We don't have storage that big. Your smartphone is never going to have capacity of 1/10 of the size of the planet. And so what is the hope, therefore, to do things with even more interesting molecules? Let's say for drug discovery, right? Those are really the molecules we want to simulate in a computer, right? We want to compute new drugs, not just discover them, right? We want to see how they interact with your body, right? We want exact drugs that do exactly what they need to do to help you with some disease, some other condition, and not, by the way, also have many bad side effects as well. So if we can't do this with classical computing, and we will never be able to keep this much information in a classic computer, are we done? Right? We've all been very spoiled over the last decades, things like Moore's Law. We keep expecting processors to be faster and faster. We expect more memory, more internet bandwidth, more storage. But here I'm telling you that this little molecule will never, ever be represented in one of our classic computers. So is that the end of computing for civilization, right? Should we just stop now? Well, I'm here. Obviously, I'm going to talk about something else. There is quantum computing, and there is a replacement for just plain bits, zeros or ones, and those are called quantum bits or qubits. We'll talk a little bit more about qubits. While it is impossible to represent caffeine using regular bits, we can represent all that information using just 160 qubits. Now, the largest quantum computer that IBM has is 50 qubits. And you can imagine, therefore, in the future, if all goes well, we will get to 160, and I hope well beyond that. So we're in a situation now, completely impossible classic computer, looks pretty likely with a quantum computer. Now, I haven't told you how I'm getting that information in there, all right, and what I'm going to do afterwards, but there's hope, right? There's hope. Part of it is because quantum computers have this exponential capability. In the classical case, which goes back to the 1940s, I would need to double the number of transistors to double the power of my processor, more or less. That's approximately it. With a quantum computer, and you see it on the right-hand side, and what's in the circle is a physical qubit. All I need to do is add just one qubit to double the power of the computer. Now, engineering-wise and manufacturing-wise, we don't just keep adding more qubits. The qubits actually talk to each other, and it gets somewhat complicated to create these, which is why we're still in only double digits numbers of qubits. But we're learning a whole lot more of that. So what happens here is we double, and we double, and we double, and we get this exponential effect. Now, because of this, and because I've said about caffeine, you would expect that there'd be some applications here for quantum computing in chemistry. And in fact, that is where many people are looking. And here, I want you to think extremely broadly with chemistry. Like you're chemical, right? You're biochemical. Everything around us. Chile exports copper, for example. How do we create new materials from copper, right? How can we design them in a computer so we don't have the trial and error of material science? So there are many different types of chemistry applications that may be useful for quantum computing, for oil and gas in the energy field, to create new catalysts, to be more environmental friendly, to use less energy as we do large-scale production of many of these things like petroleum products. The second area is artificial intelligence. Now, you'll hear about artificial intelligence throughout the conference. Many applications, parts of it go back to the 1930s, frankly. But this is a good example of two ways in which quantum computing may be applied in several areas. So the first part of this is to say, well, in artificial intelligence, way down deep, it's math. That's the whole, I'm a mathematician. Everything down deep is math, right? But it's really true. We can ask this question to say, can we use quantum computing to significantly speed up the calculations for what we do today with artificial intelligence? And there's some hope for that. But even more exciting to me is to say, because quantum computing is not just a little bit different from classical computers. Classical computers at the lowest level of bits and zeros and ones use binary logic. Quantum computers do not. They use operations from quantum mechanics. And there are interesting properties, things like superposition and entanglement and operations like interference. Algorithms are not slightly different from classical computing algorithms. You have to look at them differently. It's almost like you have to keep multiple dimensions in your head as you're trying to get rid of the bad solution, so eventually you will get to the best possible solution, or at least probabilistically so. So because it is a different way of viewing everything, you can say, can I use entanglement to somehow pull out the patterns from the data that would have been otherwise very expensive, very inefficient to do classically? And then the final area is financial services. And this, again, is an example of something which is a little bit more general. So here you might imagine international banks, investment houses, or even possibly your own investments here, can we do a better job of assessing the risk in these portfolios in a very rapidly changing world where many different things depend and influence each other? Can we do a better way of modeling this world much more efficiently with fewer samples and find those rare events, those rare, let's say, weather events that in fact may influence the risk to many different types of business? So you see, quantum computing with this, and if you think about other industries, could be quite applicable in many areas. Now, I say could be because it is likely going to be 2 to 4 years before our machines are powerful enough to say, right here, a quantum computer is significantly faster than anything we can do classically. So there is nothing today, and I'm being honest with you, there is nothing today that you can do on a quantum computer that you can also do on a classical computer. Our quantum computers are not powerful enough today, but we are making them more powerful. And we are predicting in the 2020s, we will go from today's phase of being quantum ready to a phase of quantum advantage, where we can say here in chemistry, here in AI, here in finance, here or in insurance, here in metallurgy, right? Here in creating new materials. Quantum computing is 1,000 times faster for some situations, or it allows us to do some things that have been impossible otherwise. Now, let's return to this exponential idea. So, 1 qubit, remember our basic information unit, can hold 2 pieces of information. That's nice. It's not that impressive. 1 holds 2. All right? 2 qubits can hold 4 pieces of information. But it's not 2 plus 2. It's 2 times 2. So with 3 qubits, we have 8 pieces of information. With 4 qubits, we would have 16. With 5 qubits, we would have 32. With 10 qubits, we would hold 1,024 pieces of information. With 20 qubits, it would be the same number, basically a million, as we would have, as you think of as in a megabyte. This is exponential growth. Now, at least in English, in the US, I will tell you that when people talk about exponential growth, they just mean really fast. It's highly inaccurate, okay? Exponential growth involves an exponent, all right? And this is the case, and this is the doubling. So that 50 qubit machine that we have, the number of pieces of information it has is that number, which is 1 quadrillion something. I have stopped trying to remember what it's called. It's a very large number, and that is a picture of a real IBM quantum computer. Now let's say we even go bigger. So I mentioned with caffeine we might get to 160 qubits. Let's go all the way up to 275. Still something which is a reasonable possibility over the next few years. When we get to a computer that has 275 qubits, the number of pieces of information it will be able to access during computation is more than the number of atoms in the observable universe. How does this work? We don't know. This is the wonders of quantum mechanics. All right, this is nature. And what we can do is we can harness nature through quantum computing, right? Without necessarily understanding way down if there are multiple universes and all these different theories. It's wonderful weekend reading And people have gotten spiritual over this, right? What is causing all this? It's good reading. But this is what we're trying to capture. Now, before we get off qubits, I don't want to leave you just thinking that only the qubit count makes a difference. There's a lot more. The qubits are laid out on a chip in 2 dimensions. Also, in quantum algorithms, the qubits interact with each other through something called entanglement. So it's what I call the dance of the qubits. As you are proceeding, they're getting really bonded to each other in different ways. Probability is involved, and the algorithm is like one great big funnel where you have every possible thing that could happen, and through your processing, all the bad possibilities fall away, and then you end up with the most probable answer. We have to physically build these qubits. So there are errors involved. We try to minimize those errors. There are errors involved between qubits. All sorts of physical questions as to how effective these qubits really are. This is often confused in the press. These are called physical qubits. The big qubits people talk about that last forever and do everything are what are called logical qubits. There's a difference between them, and that's important when we talk about things like cryptography. So let's now just go to ancient history in quantum computing. 2016. All right? And I want you to look at these 2 different photos. On the left-hand side, 73 years ago. That is an ENIAC computer. Note the wires. This was the beginning of classic computers. This is the great-great-great-great-grandmother or grandfather of your smartphone on the left. That is what a quantum computer looked like from IBM in 2016. And we had gotten it stable enough so that we could make it available on the cloud. Who was going to care when we did this? May 4th, 2016, we put it up there. Since that time, over 100,000 people have tried quantum computing. The IBM Q experience is completely free. You can go home this afternoon and use a real quantum computer. There's a 5 and a 16 qubit computer available, a drag and drop environment, a programming environment called QuizKit. You can get up and running using quantum computing wherever you are in the world. And it's been used on all 7 continents. There was a scientist in Antarctica who used it and then wrote a book about her experience using it from afar. So you have no excuses if you want to use a quantum computer to actually going and using it. So I'm going to go back just to refresh this. 2016, 3 years ago. Well, this is what we announced last week. Things are evolving kind of quickly. This is the IBM Q System 1. We've gone from just thinking about wires and electronics and chips to full quantum computing systems that can be put in cloud data centers. I think you'll agree it's a little different from where we've gone. And it's beautiful too, because you can have great technology with great form. So let's do it. We're inventing a whole new type of computing. So we are going to put the best we can do in 2019 and beyond into its hardware, into its technology, into its software, as well as the design. Now, thinking about this, right, we have to think about it as a full system. So with that last picture in mind, right, we have to think about the cryogenics. We have to think about the electronics that go into this, the software at the low level, and how to connect this securely to the cloud. So with quantum computing, we don't just worry about qubits, we worry about everything. And we have this wonderful freedom to do it right without being bound by the way we did it before. Many people around the world are using it today, These are some examples of companies, universities, who have joined us in the IBM Q network. In total, there are 44. There's a great opportunity for startups to get in there and start using it. And I think you'll see many names that you will recognize. Now, I want to end here by thinking about quantum computing and education. So you have many fine universities here in Chile, right? And I've told you that the IBM Q experience is free. If you wish, you can join the more formal program, the Q network, get access to the latest machines. But on the free machines, over 130 scientific papers have been written. There is nothing preventing advanced research in quantum computing in Chile or anywhere else. Maybe some funding, whoever's listening. And then finally, actually teaching this. This is going to be really important, folks. All right? This is something that people will need to learn. The best classical software engineer has no insight as to how to be a great quantum software engineer. So let's start teaching this in the universities. And you don't need a whole class. If you have a single class on computer architecture, or in applied math or chemistry, start inserting quantum. Start inserting quantum computing. Because you can today, and we need to get ready. Because if you think about it, I told you 3 to 5 years is when we'll really start having this quantum advantage. And this is perfect for university students, graduate students, and it will allow anyone in the world to take advantage of this. So there are many ways to learn more about this, but that's all I have for today. So thank you very much. Muchas gracias.